Following our discussion of how we can get non-dimensional parameters using the Buckingham-Pi theorem, we now go into video 3 to discuss how we can non-dimensionalize some of the basic equations from chapter 4. And the two main equations that we derived in chapter 4 were the continuity equation and the Navier-Stokes equation for momentum. And looking at those, we can actually try to non-dimensionalize these as well. So we know that all the terms in the above equation, so if we look at everything in the above equations, all the terms do not include temperature. So we can say that all the terms are in terms of mass, length, and time. And what we can apply to it is we can therefore say that we can apply mass, length, and time on p, velocity, x, y, and z, any position parameter, and t for time. And we can non-dimensionalize all these parameters by using density and two constants, essentially. Okay, so we're going to non-dimensionalize by using the term for density and two other constants which we're going to define. Okay, and having a non-dimensional equation means that then we can analyze a flow non-dimensionally in an experimental way and use these simpler equations and simpler relations to solve a problem, essentially. Because we know the Navier-Stokes equation cannot be solved directly, so by having a different way of looking at it, we might be able to solve it from an experimental standpoint. So these two constants that we're going to talk about is our reference velocity. So we're going to have a reference velocity for a flow called U. Okay, it's a capital U. And we're going to have a reference length called L. Okay, those are going to be our two reference constants. And U, for example, could be in a specific flow, could be, for example, the inlet velocity. Okay, and L could, for example, be the diameter of the body if it's, for example, something circular in shape. Okay, these are reference dimensions within a flow, so they stay constant. Okay, so we can write that these are specific to a particular flow. But we usually use velocity and length of a body. So moving forward from that, we can now try to non-dimensionalize our equation in the following way. So we can say that a new non-dimensional variable is going to be called v star. So we're going to have v star is equal to the velocity at that point in the flow over u. And we can clearly see that that's non-dimensional. We're also going to say that the gradient star is going to be equal to length times the gradient. Okay, so once again, a dimensional parameter. And we're not going to go through the derivation of this because it would take a lot of time, and using the Buckingham-Pi theorem to prove all this could be a whole textbook in itself. So we're just going to take it for granted that these are correct. But if you actually work through the equations, you'll see that you'll get non-dimensional parameters. We can also call a non-dimensional parameter called x star, and x star can be equal to x over L, y star, which is equal to y over L, z star, which is equal to z over L, once again, all non-dimensional. Time star in non-dimensional form would be t times u over length. Okay, velocity over length times time yields time times time minus to the minus 1. And pressure star is equal to pressure plus rho, which is our third parameter. Okay, let's not forget rho as our third parameter. Okay, that's our third non-dimensionalizing parameter, times gz over rho u squared. And so we can rewrite our continuity equation above and our Navier-Stokes equation in the following manner. If we have all these non-dimensional parameters, we can now say that since they're non-dimensional, we can say that the gradient star times v star is equal to 0, and dv star over dt is equal to negative, and this dt has also a star on it, okay, is equal to negative gradient star p star plus, in order to work this out to be unitless, we actually have a term that is plus mu over rho u L. And we should recognize this term, okay? We should be able to recognize this term. So let's look at it in a little bit. And then we have gradient star squared multiplied by velocity star multiplied by velocity star. Okay, so that's our continuity and momentum non-dimensionalized. And we can see that this Navier-Stokes equation yields that we have this term here, and this term is actually 1 over Reynolds. We remember that Reynolds number is equal to rho times u times L over mu. Okay, if we use u for velocity instead of v for velocity, since we defined u as our reference velocity. Okay, so we've developed a new way to use non-dimensional parameters to define our continuity and momentum equation. Now, in this class, we're not really going to apply this to anything, but it is good to know this and to know where this number comes from, this Reynolds number comes from. Now, going further than this, if we look at the boundaries of our flow, so if we actually look at boundaries of flow, we actually get at our free surface, okay, so in our free surface environment, which is one of the boundaries, we can say that P star is equal to pressure atmospheric over rho u squared plus GL over u squared times Z star minus Y over rho times u squared L times Rx star, not R star X. So it's Rx star to the minus 1 plus Ry star to the minus 1. And this term right here, okay, and this equation you don't have to remember, okay, this is just to show you at a free surface what you would get for your pressure term. This number here is called the Weber number. And this Weber number is really used for, so the Weber number is actually the opposite. So it's 1 over the Weber number. And the Weber number is rho u squared L over y, capital Y. And this capital Y is actually surface tension. It is a value for surface tension. And this term for surface tension actually is used in case when we are looking at high curvature flows on surface. So if we're looking for the pressure of high curvature flows on a surface, we can actually use this Weber number to try and solve our problems in a non-dimensional way when we're doing some experiments. Okay, this gets pretty complex, and it uses the fact that at the free surface we have some interesting relations, which we looked at a little bit in chapter 4. We also have, for general free surface flow, we also use the Froude number. Okay, this is the Froude number. And the Froude number is just equal to u squared over GL. And we see that in our equation above, we also have 1 over the Froude number. So this Froude number is used in free surface flows. So for example, if you have a free surface flow in the ocean and you have a velocity of a ship vessel on the flow and you have a certain length, you can use the Froude number to scale your experiment to a different size and do an experiment with a much smaller boat. And as long as you keep your Froude number constant, you can therefore decide, okay, my Froude number is constant, therefore I can do an experiment on a smaller boat that would yield the same u squared over GL. So it's very useful in scaling experiments. So it's used to scale experiments. And all these parameters are really used for that reason. Okay, so just to summarize, we have a few dimensionless parameters. So the first dimensionless parameter that we can talk about is the one that comes from Navier-Stokes equation. And it's that Reynolds is equal to rho UL over mu. And if we keep Reynolds constant in an experimental test at different sizes, we get the same flow characteristics in our flow. If we keep rho UL over mu constant with different sized experiments, we're going to get the same exact flow in a submerged flow. This is submerged flow. So we need a flow that is completely submerged without a free surface. Okay, so it's usually in a region where you have just a completely submerged flow. Now, the Froude number is used on the surface. So Froude number is equal to u squared over GL. And this one is used in free surface flow. So whenever we have flow, but on a surface. We then also have the Weber number. So Weber number is WE is equal to rho u squared L over Y, which looks at the effect of surface tension, and it usually looks at surface waves, open channels, and ship resistance. Okay, it's usually used in these types of flows. Now, we're not going to go into more detail on this, but it is pretty interesting to look at. The Froude number, we're also not going to go into a lot of detail in because that is in chapter 10 in your book, and chapter 10 is not covered in this class as well. So, but if you want to learn more about it, you can go to chapter 10. We also have the Euler equation, which we haven't really talked about and is not really used much because it uses, so it's called the Euler number, and it's not really used much because it's only used in case of vapor formation. So whenever you have vapor formation within a flow. So that's the Euler number. I'll still write it down just so you have it. So Euler number is EU and is equal to pressure atmosphere over rho U squared, but it's only used in vapor formation flow. And we're not really going to be looking at vapor formation in this class. So it is rarely used. This is also called cavitation if you want to look more about it. Okay, and the final number that we're going to look at is a compressibility parameter. And this compressibility parameter is going to be the Mach number. And this Mach number is U over A. So that's one of them. The Mach number is named after Ernst Mach and is used to relate our velocity of our flow, our U, over A, which is the speed of sound. Okay, we've already defined this earlier. The other compressibility parameter that we have to take into account for flow at very, very high speeds, so this is for high speed gas flow, so for example, when a jet fighter flies over Mach 1, it means that the velocity is faster than the speed of sound. And so we need to have some relations to talk about our compressibility during those types of flows. The other one is called the specific heat ratio, which we also have to satisfy when we have a high-speed flow. And the specific heat ratio is called K, which is Cp over Cv. And that's essentially the specific heat at constant pressure over the specific heat at constant volume. Now, the specific heat at constant pressure and constant volume is defined as the amount of heat it takes at constant pressure to increase 1 kilogram of a certain substance by 1 degree Kelvin or 1 degree Celsius. And Cv is the same at constant volume. And you have a list of all the dimensionless groups in fluid mechanics in table 5.2. So if you want to look at all the different ones that we use in fluid mechanics, generally, they're summarized in table 5.2. Okay, so if we apply our dimensional analysis to any problem, we can then come up with an idea of what is happening in our system. Now, just to go a little bit more on the Mach number, one more thing that I want to talk about in the Mach number is that there is an effect on compressibility when Mach is greater than or equal to 0.3. So if we have a relatively low speed, the Mach number is not important. If we get to higher speeds and we see that Mach number is 0.7 or 0.8, which means that our speed is very close to the speed of sound, we now have to take into account our Mach number as a way to compare different flows. And we'll be looking at this in our final module for the semester as well. So that'll be interesting. So if, for example, we decide that we want to look our dimensional analysis, we want to apply dimensional analysis to any problem, we can say, why don't we look at a certain flow, for example, around a sphere, and we have what we called submerged flow, so flow that is completely submerged in air, for example, or in some other fluid. And we have a certain force that's created on this sphere that is being pushed. Okay, so this is a sphere, and we have some flow going around a sphere. Now, if we look at this system, we can say that we have normal flow. So the flow is normal to the sphere. Okay, it's going towards the sphere. We can say that the normal force created by this flow is equal to the drag force. And we also know that the sphere, and I'm going to draw it in orange here, the sphere has a cross-sectional area. Okay, so it's a cross-sectional area. Okay, it has a cross-sectional area, and this cross-sectional area has, for example, we know it has a certain length, and it has, or we can say it has a diameter, a length or a diameter, whichever way we want to call it. So it has diameter. So if we look at the front side of this, we can find this area by saying that this is equal to pi times d squared over 4. So it's pi over 4 d squared, or L squared if you want to use length. And that means that we can actually come up with a coefficient of force, which in this case is equal to a coefficient of drag, because our normal force is equal to drag, that is equal to the drag force, so the actual force, so the drag force, divided by 1/2 rho v squared times pi over 4 times d times d. And I'm leaving this as times d because I want this to be clear that we're multiplying d by d. And so if we had a different shape, we would just multiply the length times the diameter, for example. But essentially what this is called the projected area. It's the projected area of our system. So by dimensional analysis, if we have a normal flow on a sphere, we can say that CD is equal to the drag divided by 1/2 rho v squared times the projected area and that means that we can actually find our coefficient of drag should be equal for all different sizes. So that means that if we, for example, half the projected area, it should mean that we also do half the drag, and we keep our CD constant. So let's actually go and look at an example of what this is in a little bit, once we start discussing what similarity means and defining what similarity is. So moving on from this was just a little example to show you how we can use non-dimensional parameters to apply to an equation. And we're actually going to be using this equation later on in the semester. But let's look first at similarity and then do an example of how similarity would work when we have two different sized objects, for example. So let's talk about similarity. So similarity means the same thing or the similar thing, right? And we're going to be looking at two different types of similarities: geometric similarity and dynamic similarity. But first, geometric. So geometric similarity is that a model and a prototype are similar if all body dimensions are scaled linearly. So we can say that a model and a prototype are similar if all body dimensions are scaled linearly. And we can go even further than this and state that for a certain system, I'm going to copy over a statement here. For a certain system, we can say that flow conditions for a model test are completely similar if all relevant dimensionless parameters have the same corresponding values for the model and prototype. Okay, now for our geometric similarity, we can apply this and look at if the prototype is the same geometric similarity as another one. So let's look at an example of this. So I'm going to copy over a diagram. And we can see in the above diagram that we have two wings, and we could be asked, are these two wings geometrically similar? So do they have geometric similarity? And the answer lies in the statement that we made above. So model and prototype are similar if all body dimensions are scaled linearly. So if we look at one dimension, which would be the width of the wing, for example, okay, we see that it's 40 meters in width. And we see that our scale wing is 4 meters in width. So can we say that they are geometrically similar or not from that statement? Well, not really. We can only say that 4 meters is 10 times smaller than 40 meters. What we need to check is all the other dimensions as well in relation. So we have to check the width, we have to check the length, and we have to check the height. And we have to make sure that they're all at the same scale. So in this case, yes, we have geometric similarity because 1/10 is the same as 4/40 and is the same as 0.8 over 8. We have a 1/10 scale model. Okay, so that's what geometric similarity means. And geometric similarity is pretty easy to understand. Now, what if we go to dynamic similarity? So dynamic similarity is the next step that we're going to be looking at, and we're going to be setting some rules for dynamic similarity. So dynamic similarity exists when the model and prototype of this have the same length scale ratios, the same time scale ratios, and the same force scale ratios. Okay, so we're adding on to our just length scale ratios. Now we're adding time and force. And I'm going to write this down so that we have it in our notes, but this exists when the model and prototype have the same length scale ratios time scale ratios and force scale ratios. Okay, so these three things have to be satisfied in order to have dynamic similarity. Now, a force scale ratio can also be thought of as a mass scale ratio, but that can be talked about in more detail after, but essentially force scale and mass scale are directly related. So you can use either force scale or mass scale in some definitions. Now, to have dynamic similarity, our first requirement is that we have geometric similarity. If we don't have geometric similarity, we cannot compare two different dynamically similar systems. It's impossible. Okay? So now we can come up with rules to say what is happening and what is going to be similar in a flow if we have incompressible flow and if we have compressible flow, given that two flows would be dynamically similar. So we can say that dynamic similarity is achieved, one, for incompressible flow, when the following happens. So for incompressible flow, and first we're going to talk with no free surface. So this is a completely submerged flow. We can say the following. We can say that Reynolds, okay, and we usually use a little d for Reynolds or a little L, it depends. But Reynolds for model and prototype are equal. So whenever we have a Reynolds number for two systems and we want them to be dynamically similar, we have to satisfy this condition for incompressible flow. Okay, we need to satisfy these conditions to say that we have dynamic similarity. So in the submerged flow, we have dynamic similarity when we have our Reynolds number for model and prototype are equal. And remember, we also need to satisfy our geometric similarity. Okay, our two shapes have to be geometrically similar in order to apply this. Now, if we have a free surface flow, so if we have with free surface, we now need to satisfy more than one equation. We need to satisfy Reynolds, RE sub D, and the Froude number. So we need to satisfy Reynolds and Froude, and they both have to be equal. Okay, so not equal to each other, but for the model and prototype have to be equal. And remember, Froude number is equal to V squared of the model over GLM. GL of the model is equal to V of the prototype squared over GL of the prototype. Okay, so that condition has to be met in addition to Reynolds number being similar as well. So now we have two conditions to satisfy. So we need to check for two conditions to make sure that something is dynamically similar. And for compressible flow, we need to check a couple of things. for compressible flow, we need to check that, we need to say that Reynolds number should be equal, Mach has to be equal between model and prototype, and K, which is equal to Cp over Cv, also have to be equal. In order to satisfy that we have dynamic similarity between a model and a prototype. So those are the three things that have to be applied. So why don't we do an example and try and figure out if an experiment can be worked for and can actually make sense in terms of doing an experiment at a smaller scale. So we're going to be doing example 5.9 from your textbook. I'm going to copy over the question. And example 5.9 says that we have a prototype airplane. And it says that a prototype airplane with a chord length of 1.6 meters is to fly at Mach is equal to 2 at 10 kilometers standard altitude. At 1/8 scale model, a 1/8 scale model is to be tested in a helium wind tunnel at 100 degrees and 1 atmosphere. Okay, so we have a prototype and a model. So the first thing we can say is we have a prototype and then we have a scale model. The model is always the smaller of the two, okay, usually. So we usually like to use smaller models in fluid mechanics. And we're told that the helium is at 100 degrees and 1 atmosphere in the wind tunnel. And we're told that to find the helium test section velocity that will match the Mach number. So the first step is we have to match the Mach number of our prototype airplane with our helium in the wind tunnel. So how are we going to do that? Well, we're going to try and figure out that our Mach number for our prototype should be equal to our Mach number for our model. Okay, that's our goal. And since we have Mach is equal to 2, since we have the fact that Mach outside is equal to 2 in our prototype, we can say that we assume we have compressible flow. Okay, we have to assume we have compressible flow because our Mach number is higher than 0.3. Okay, we had a rule that if the Mach number is greater than 0.3, we have compressible flow. And we can say that Mach is equal to velocity over A, which is our speed of sound. So the great thing about this problem is we're given that the Mach should be similar, and we have to figure out the velocity in the wind tunnel. Now, we already know our Mach number, so we can say that the Mach number for air, or the Mach number for our prototype, should be equal to the Mach number for helium, which should be equal to 2. And so we can write that this is equal to velocity of the helium over A of the helium. A being the speed of sound of helium. Okay, so we already know the Mach for air, so we don't need to figure out the velocity of air. We just need to figure out the side of the helium. We just need to find the velocity of the helium. So we have that 2, if we use this side of the equation, we have that 2 is equal to velocity of helium times A of helium. So if we can find the speed of sound for helium, we can therefore find our velocity of helium. So for the speed of sound of helium, what we're going to be doing is we're going to be saying that the speed of sound of helium is equal to square root of kRt. This is our equation for speed of sound Okay, so that's our governing equation for speed of sound. If we can find all the values in that equation for helium, then we can solve this problem. So we already have the temperature of helium. Okay, so that's all good, but we need to find K and R. Now in the question, we don't have any information on K and R, so we're gonna have to find it. So in order to find it, we're going to have to go to our fluids appendix. And in table A4, we actually have some information about helium. Now, what you can see here is that we have a couple of things. So we have table A4, and it gives us properties of gases at 1 atmosphere and 20 degrees Celsius. Now, at 1 atmosphere and 20 degrees Celsius, we have that helium, the ratio of specific heats, is equal to 1.66. Now, we also know that our temperature is not 20 degrees, but in our tables, we don't really have other values for helium other than looking them up online or on another source if needed. But here we have our specific heat ratio, and we also have our R term. Now, in our case, because we only have a table with one value at one given temperature, we're going to be using this table, okay? Now, if you were in a thermodynamics class where temperature is very important and the ratio of specific heats might be a little bit more important, you can go and look at values at the given temperature of 100 degrees. But for now, we can assume that this will be close enough. The values of R and specific heat do not change that much with temperature anyways. Okay, so we go there, we find our specific heat ratio, we find our R, and we go back to our terms here, and we can now plug in to our equation with K is equal to 1.66. So from table A4, so in our appendix, 1.66 times 2077 multiplied by the temperature in Kelvin. Okay, it's very important to convert to Kelvin. And you can use 273 to convert to Kelvin in this class. You don't have to use 273.15. It's up to you. 273 is fine for me. And so you would get that the speed of sound is 1,134 meters per second for helium. So we can now go and say that our velocity of the helium is equal to 2 multiplied by A of helium, which is equal to 2,268 meters per second. So essentially, in order to match what is happening, in order to match what the Mach number is, we would have to, in order to match the Mach number, we have to use a speed of 2,268 meters per second for our model. Okay, so that's the first step in our problem. Now, in part B of our problem, we are told to find the helium test section velocity that will match the Reynolds number for the prototype. So the next step is to look at and find the Reynolds number of the prototype. So we're going to do the same exact analysis, but now we're going to be looking at the Reynolds number. And the Reynolds number equation is the following. We have that Reynolds of the prototype, or of the air, is equal to rho V times C over mu for the air, and Reynolds for our model, which is using helium, is equal to rho times velocity times C over mu for helium. And what is our value for C? Well, C is actually a length, and this length is called C because for a wing, we usually use the chord length to determine our length that we use as a comparison factor. And just like we were using the diameter of a sphere earlier in an example, in this case, the chord length of a wing, so if I draw the side of a wing, the chord length is the length from this point to this point through the middle of the wing. So that would be our value for C, our value for chord length. And that's going to be used to dimensionalize both systems together. So what we have to do is we have to see if Reynolds matches between the two systems. So the first thing we can do is we can work on Reynolds for air. So let's look at the Reynolds for air first. So we have that Reynolds for air is equal to rho times V times C over mu for air. And we're going to have to find a bunch of different parameters in order to solve for the problem. So some of the information that we're given for the air is the following. So we're given that we have a prototype airplane flying at 10 kilometers standard altitude. Okay, and this 10 kilometers standard altitude is actually going to be important. And we know that the Mach is equal to 2. So we have that Mach is equal to 2, and we have 10,000 meters or 10 kilometers altitude. And with this information, we're actually going to be able to find our density of air at that height. We're going to be able to find our velocity or our speed of sound at that height, which means we know that our velocity of the air is going to be equal to 2 times a air. Okay, it's 2 Mach 2 multiplied by the speed of sound. And we're also going to be able to find the viscosity of air. So moving forward from there, let's go to our tables and our appendix to see where we can find this information. So if we go to table A6, table A6 in our system, we can actually see that we have properties of standard atmosphere at different heights. So we have properties of standard atmosphere at different heights, and Z is the height of that atmosphere. And we see that we have 10,000 meters, and at 10,000 meters, we're given certain values. So we're given density, okay, and we're given our speed of sound. So we can use those two values in order to find our velocity of our air. So if we go back to our system here, we can say that from table A6, density of air is equal to 0.4125, and the speed of sound of air is 299.5 meters per second. Therefore, the velocity of our air is going to be 599 meters per second. And if we look further than that, we also have to find our viscosity of our air. So going back, we don't really have a term for viscosity in this table. So what we have to do is to go back to a previous table and try to figure out what our viscosity would be. So we see that for air, we have a viscosity that is shown in table A3 or A4. So we're going to be using table A4. And for our air, we're actually going to be able to use this table to figure out what our viscosity is. And our viscosity is shown right here. So you can see that our viscosity for our air is given in this chart right here. So this viscosity is for gas at 1 atmosphere and 20 degrees Celsius. Now, that's clearly incorrect. Our gas is not at 1 atmosphere and 20 degrees Celsius, and it actually is probably pretty far off from that. And viscosity actually is affected a lot by those systems. So what we're going to have to use is this little equation at the bottom of our table that says that mu over mu at 293 Kelvin is equal to T over 293 to the power of N. Now, what is our temperature of our air? If we go back to our problem, we can go look and we're not really given a temperature for our air. However, in our problem, we know that we're at 10,000 meter altitude. So we can use our values for our standard values for 10,000 meter altitude, and we can see that at 10,000 meters, we have a certain value for temperature, which is quite different from 20 degrees Celsius. Okay, 20 degrees Celsius is 293 Kelvin. We see that at 10,000 meters, we have 223 Kelvin. So a big difference. So we need to take this difference into account by applying this correction factor to the system. So we have that value. We also have the exponent n, which is given here. And so if you plug in your exponent n and your temperature for table A6, you get that this would be equal to 1.48 times 10 to the minus 5 Newton seconds per meter squared. Okay, very important. So going back to our diagram, we can say that mu air is equal to 1.48 times 10 to the minus 5 Newton seconds per meter squared from table A4 and A6. And this is using power law under table A4. Okay, so we can see that the viscosity of air changes from 1.8 at 20 degrees Celsius to 1.48. So it's not something that we can ignore. So now we can find that the Reynolds of air is equal to 0.4125 multiplied by 599 multiplied by 1.6, which is our chord length, divided by 1.48 times 10 to the minus 5. So we have that this is equal to 26.6 times 10 to the 6. Okay, so that's our dimensionless parameter Reynolds air. So now that we have this, we can say, okay, so the next step is to figure out what we get for our Reynolds for helium. But another way to say it is we can say if we're supposed to have Reynolds similarity, then that means that Reynolds of air should be equal to Reynolds of helium. So what we can do is we can sort of calculate and say, well, if this happens, then we have the Reynolds number for the prototype and the model would be matching. Okay, so the matching velocity has to be found from this. So we can say that 26.6 times 10 to the 6 should be equal to rho of model times v of model times c model over mu of model. Okay, and we can find this by saying, what is our C of model? So let's try and find C of model, the first thing. So C is the chord length of the model. It says that a 1/8 scale model is to be tested. So since it's a 1/8 scale, we know that Cm is going to be equal to 1/8 multiplied by 1.6, which is our chord length for our original prototype. So we have that this is equal to 0.2. So Cm is equal to 0.2 meters. Now, for the density of helium, we don't really have it from the tables, so we can say density of helium is equal to pressure over R times T from ideal gas. So we're not given the density of helium in the table, so we can actually find it from ideal gas. So we can say that our pressure is going to be standard atmosphere, so 101,325 divided by 2077, which we had found earlier, multiplied by 373, which is our temperature, 100 degrees Celsius plus 273 to convert. So we can say that the density of helium, okay, from our ideal gas equation is equal to 0.131 kilograms per meters cubed. And our mu can be found from our table A4. So if we go to table A4, we have helium, which is 1.97 times 10 to the minus 5. We then apply the correction factor for the temperature. So we now have a temperature, so we apply the same correction factor with a temperature of, I'll write it down here, we have a temperature of 100 degrees Celsius. So we apply the same equation and we apply this to the same equation with our N now for helium, so 0.67, which is actually the same power law exponent. And we get that mu is equal to 2.32 times 10 to the minus 5. Okay, so it's really important to know that mu has to be changed with that power law as well. Okay, so we use that power law in the same way. Okay, and I'll let you do that in your own time to make sure that you know how to do it. So now that we have the values, we have everything except for velocity. So we can say that this is equal to 0.131 times 0.2 times velocity of helium divided by 2.32 times 10 to the minus 5. And we see that the velocity of helium is equal to 23,600 meters per second. So in order to achieve Reynolds similarity, our velocity of the helium should be equal to 23,600 meters per second. Okay, if we look at it above and we look at the velocity that was required for the Mach number, we know that the velocity required to satisfy the Mach number is equal to 2,268. So one says 23,600 meters per second, the other one says 2,268. So what we can write from this is that our Reynolds matched velocity does not match Mach similarity. So we have a problem. If we use our system and we try and have Mach and Reynolds number of the prototype, we actually get into a problem where we can't really solve our problem. We can't have both happening at the same time. So find the helium test section velocity that will match A, the Mach number, or B, the Reynolds number of the prototype. There's two different velocities. So in each case, it says to criticize the lack of dynamic similarity. So the lack of dynamic similarity in our Reynolds number problem is the fact that it does not match Mach. And since we have a flow that is above Mach equals 0.3, we therefore have a system that essentially a system that is compressible. So we have to have Mach and Reynolds number matching together. In this case, they don't. So both of them don't match. So that's what we can say about the Mach similarity. Now, what's another thing we can say? So about geometric similarity, the other requirement for dynamic similarity, not geometric, but for dynamic similarity, we remember for a compressible flow, we have three conditions. One condition is to say Reynolds of air, or let's say Reynolds of the prototype instead. So Reynolds of prototype should be equal to Reynolds of model. Then we have Mach of prototype is equal to Mach of the model, which is not satisfied. Okay, those things are not satisfied because we have a different velocity for both to be satisfied. And the third one is that K is equal to Cp over Cv. Okay, and if we look at the K for air and helium, we actually find out that the K, which is our specific heat ratio for air, is 1.4 and for helium is 1.66. So we can go further with this and say that K of prototype is not equal to K of model. So this is not satisfied as well. So we can say with certainty that we do not have dynamic similarity. Okay, now in the last part of our problem, we are asked what high pressure in the helium tunnel will match both the Mach and Reynolds numbers. So now we're asked what high pressure in the wind tunnel or in the helium tunnel will match both Mach and Reynolds number. So let's try and solve how we would do this. So if we need to match Mach number, so in part C, we're going to say, how can we match the Reynolds and Mach? Well, the Mach can't change. So that means that if the Mach number can't change, we know that the velocity of the helium has to be 2,268 meters per second. There's no other way. So that means we can change the Reynolds number of our system to try and match with our Mach number. So what we can say is we can actually change our pressure in our system to make our Reynolds number equal to 26.6 times 10 to the 6. So the Reynolds for the prototype cannot be changed, okay? And the Reynolds for the prototype is 26.6 times 10 to the 6. So the idea is to try and make our model match what the Reynolds would be with a velocity of 2,268. Okay, so with a velocity of 2,268, we want to try and match our Reynolds. And that means that we can say that this should be equal to density multiplied by V helium multiplied by Cm divided by mu of helium. Okay, and in order to do that, what we actually have to do is we have to figure out, using these values, we have to figure out a new value for pressure. Now, pressure is not directly in the equation, but we know that the pressure of helium is equal to density times RT from ideal gas. So from this, we can say that pressure is going to affect density. So if we change the pressure, we might be able to achieve a new density that will allow us to have a Reynolds value of 26.6. So what we can say is, let's try and find a density that can allow us to get 26.6. So if we rearrange the equation, we can say that this is equal to, so this equation is equal to density times the velocity of helium is now 2,268 multiplied by 0.2 divided by 2.32 times 10 to the minus 5. And if we rearrange, we find that the density of helium, in order to make that match, should be equal to 1.36 kilograms per meters cubed. Now, in order to make that happen, well, we need a different pressure in our tunnel. So our pressure in our tunnel is now equal to 1.36 multiplied by 2,077 multiplied by 373. And we get that our pressure in our tunnel should be 1,050,000 pascals, or 1.05 times 10 to the power of 6 pascals. So now, with a higher pressure, we've changed our system to make it so that Mach and Reynolds are now satisfied. So we've increased the pressure in our system in order to satisfy Mach and Reynolds. The problem is that in part D, we're told, why does part C still not achieve dynamic similarity? Well, it still doesn't achieve dynamic similarity because our K for air and our K for helium are not equal. Therefore, we do not have dynamic similarity. So if we go even further than this, then in order to get dynamic similarity, we would have to use air for both systems. So we would have to change our helium to air. So we would have to change helium to air and then figure out what pressure of air would be needed in order to have our Mach and Reynolds now satisfied. So this was problem 5.9. So you can look at the solution in your book. Your solution in your book is a little bit shorter, but can help you look at the problem in a little bit of a different way as well. And this concludes our discussion of Module 5. In the next module, we're going to be looking at viscous flow in pipes. And we're going to start the module by looking at some videos and then finishing off the module by some live lecture work. So we'll see you in Module 6.